So there's a lot of things that are much easier to analyze and work with if they're in polar coordinates. And the polar form of the equation of a parabola and a hyperbola, an ellipse, all kind of boil down to the same kind of thing. Before we get going with that stuff in section 10.6, let me bring you up to speed on orbital mechanics. We're going to talk about ellipses and how you maneuver in space. So let's just give this a quick 50 seconds.
Speed slowest at the top. In space, you'll be orbiting a body slower at your highest point and faster at your lowest point. And if you have the same orbital path as something else, that already means you're going at the same velocity, and speeding up or slowing down will actually mean you're just changing the shape of your orbit. So you can't actually catch up to something if you're orbiting on the same path, because your velocities are fixed. Instead, you could just slow down to shrink your orbit, essentially creating a shortcut to intercept your objective, and then speed back up so that you stay in the same orbit. And if we're orbiting in a circle and we just want to get to a higher orbit, we need to first fire our engines forward to raise our orbit on the opposite end, and then wait until we reach that high point and fire our engines again to circularize it. So firing our engines directly towards the destination won't really work because we're already going really fast in a totally different direction. Instead, we want to just add to the velocity we've already gained and let gravity itself direct us to the destination.
So pretty cool. And I've experienced some of that stuff myself. If you ever go to a velodrome, you can change your speed just by moving up and down some of the steep banks on your bike. So pretty cool stuff. But when you're in space, you're moving in an elliptical shaped path. And the ellipse, like all of our conic sections, can be modeled in polar form this way. It's going to be R equals E times D over 1 plus or minus E cosine of theta. Or likewise, you could replace that cosine of theta with a sine of theta and get a different equation, but still going to be a polar equation, ED over 1 plus or minus E sine of theta. All right, so there's your polar equations in, those are your conic equations in polar forms. But a couple questions here. For instance, what's E? E is the eccentricity. Eccentricity. And that talks about the shape of your orbit or shape of your conic section. Now, eccentricity is probably best demonstrated with an ellipse. I'll give you a couple more seconds to finish copying this down, and we'll look back at the eccentricity of an ellipse, see and understand that. And we can also apply it to the Earth and one of the comets that's orbiting our sun right now, Comet Neowise. Maybe some of you guys have had a chance to spot that in the nighttime sky. It's been the brightest comet, I think, since Hale-Bopp, which passed us in 1997. All right, so let's flip over here. So we'll start out with this graph, which is a circle. And I'll kind of zoom in a little bit. Don't want to zoom in too much. But as I move this slider, the shape of this circle is going to change into an ellipse. And the more I move the slider, the more eccentric it becomes. Now, the eccentricity is really just a ratio between C, which is here, which you're going to use to calculate how far away from the center your focus is, that distance, and the length of your major semi-axis. So that would be the distance between the origin, and at this point right here would be at 4. So that'd be that distance between the center and your vertice on your major axis. So let's watch as this gets more and more eccentric. So right now the eccentricity is right here at 0.77. That's pretty eccentric, but you can get even more and more eccentric, and the eccentricity can get really, really close to 1. And right now, Comet Neowise has an eccentric orbit with an eccentricity even more eccentric than this, about 0.99 something. I think it says like 0.9996, something like that. So what you can see here is that as neowise passes the sun, it does so in a really, really tight orbit. Now, that eccentricity is the same eccentricity we saw with parabolas. We started out with the shape of a parabola being defined by the place where this distance to the focus and this distance to the directrix are the same for all points on the parabola. Now, when you're moving to an ellipse or hyperbola, then that ratio changes. Let me see if I can't dig that out of our calc book here. Let's see. No. So let's cut back over here. So that distance, let's see, right there. There we go. So the eccentricity, that E term in our polar equations is going to be less than 1. That means you're going to be dealing with an ellipse. If it equals 1, that's going to be a parabola. And if it's greater than 1, then you've got a hyperbola for your shape. So we'll have to pay attention to that. We'll also pay attention to that D that I put up in my equations, because that's going to help us determine the directrix. Each of our polar graphs, each of our conic sections is going to have a directrix, one directrix, defined by that D. Let's see. So let's start out with this example. Now, in order to try and make sense of this and determine all of this stuff, the first thing I'm going to do is I need to make this a 1, just so that it lines up pretty nice with these formulas. So we'll do that. R equals 8/6 plus cosine of theta. If I want to make that a 1, what I can do is multiply both the numerator and denominator by the same thing, 1/6. Now in the numerator, that's going to give me 8/6, which of course is also 4/3. And in the denominator, I get 1 plus 1/6 cosine of theta. What's nice about writing it like this is I can immediately see what the eccentricity is. So the eccentricity is 1/6. Now, what kind of a conic section does that tell you that we're going to work with? You remember you had 3 choices. You had an ellipse, a parabola, and a hyperbola.
Ellipse.
Good. Yeah, it's going to be an ellipse. That's going to happen when the eccentricity is less than 1. So we got eccentricity of 1. And there's one last thing we need to determine, and that's the equation of the directrix. So let me try and help you find the equation of the directrix. Your directrix, for this, it's going to have the equation of x is plus or minus d, and the plus or minus is going to match the plus or minus in here. So if I had 1 plus 1/6 cosine of theta, then I'd have a plus here for my equation of the directrix. Now, if you have a sine instead of a cosine down here, if you have a sine goes with the y coordinate. That's my new little mnemonic for myself for remembering these things. Cosine goes with your x coordinate. Sine goes with your y coordinate. So this is going to be y equals plus or minus d. So you're going to have a horizontal directrix as opposed to a vertical directrix. And again, the sign down here will match S-I-G-N, not S-I-N-E. Sine matches. So what we got to figure out is, okay, well, what's D? Because what we've got right now in the numerator is really E times D. So we need to peel off the E to figure out what D is. Let's rewrite that as 4/3 over 1 plus 1/6 cosine of theta. And that numerator is E times D. Okay, so let's think. 4/3 equals E times D, but there's good news here. I know what E is. E is 1/6. So I can use that to figure out what D is. Multiply both sides by the reciprocal, and I find that D equals 8. Now, because I've got a cosine here, in fact, I got a plus cosine, together with that D, that tells me my directrix is x equals 8. And that's all that they can ask you in terms of, you know, polar equation of a conic like this. They'll ask you these kind of things. One thing I should mention here is that these are set up so that the focus is at 0, 0, which is also called the pole. You'll see it called the pole in the book. Sometimes they'll ask you to write pole instead of 0, 0. But these all assume that you have one focus at the pole.
What were the conditions for if it's an ellipse parabola or a hyperbola?
So an ellipse means that E is less than 1. Here E equals 1 and E is greater than 1. Those are the conditions for hyperbola, parabola, and ellipse. And in our case, E was 1/6, so that's why we got an ellipse. So in order for this denominator to equal 0, this number has to be at least as big as 1, if not greater than 1. Otherwise, I'll have 1 minus 1/6 or 1 plus 1/6 at most, because remember, cosine and sine go between 0 and 1. So if this isn't at least 1, I'll never divide by 0, and I'll just get a nice ellipse. But it's when I get a 0 here that that ellipse busts apart. And then I get a parabola or a hyperbola. So that's kind of what I think of it in terms of this being less than or equal to 1 is an ellipse. Let's do another one. So we'll call that one example A. Example A. Let's move on to example B. In this case, we'll start with R equals 18 over 2 plus 3 sine of theta. And kind of like the last one, we're going to start out by figuring out what the general form of the equation looks like, or the standard form of the equation, I probably should say. Any suggestions as to how to start that process? What would you do to get it in our standard form?
18 divided by 2.
Yeah. So we're going to divide everything by 2, or multiply, say, by 1/2. So I'm going to multiply by 1/2 over 1/2, because effectively I'm multiplying by 1 when I do that. And when I do that, instead of canceling this, I'll just distribute in the denominator and multiply in the numerator. That's going to give me 9 over 1 plus 3/2 sine of theta. Okay, nice. Let's find a few things here. We're going to find what type of conic section this is. We're going to find the eccentricity. Maybe I should write those in a different order. We're going to find the directrix. And we'll also find, let's see, I want to say that one for the next one. Yeah, well, let's start with this. I'm trying to think if I want to add one more thing to this. Yeah, but let's start with this. What's the eccentricity here? Can anyone read that off?
It's 3 over 2.
Yeah. Perfect. Eccentricity is 3 over 2. All right, so 3 over 2. Nice. And if the eccentricity is 3 over 2, someone else tell me what type of conic section I'm dealing with.
Hyperbola.
Going to be a hyperbola. Thank you. And last but not least, we need to figure out the directrix. So the numerator is going to equal 9 equals E times D, or equals 3/2 times D. If you solve by multiplying both sides by 2/3, 2/3 times 9 equals 2/3 times 3/2 times D. You get 6 for D. Okay. Not bad, not bad. But we're not quite done here. That's just telling me what D is. It's not giving me the equation. So a couple things I know about the equation. First of all, is it going to be an x equals something or y equals something?
Y equals something.
Yeah.
Why?
Because sine goes with a y coordinate, cosine would go with an x coordinate. So it's going to be y equals 6. It's going to be a positive 6 because this is a positive here in the denominator. So y equals a positive 6. You don't have to write the positive. And that's going to be your directrix. Nice. Desmos can graph these. You can graph these things on your graphing calculator. Let's see, do I have this one plotted out? Thought I had one open for that. $10.6, there we go. So one thing you might want to do when you're working with Desmos is switch the grids. You can switch to polar grid, which makes things nice. And then we can plot some points there. You can plot your equation. R equals 18 plus 2 sine theta, 2 plus 3 sine theta, and we get a hyperbola. And should be able to zoom out enough. There we go. You see both branches of the hyperbola. Now, what if you wanted to find the vertices of this? Well, we can do that. We can do that by figuring out what's going to happen when theta equals, say, pi over 2, and theta equals 3 pi over 2. Those would be kind of the extremes here that would give us our vertices. So let's find the vertices. At theta equals pi over 2. At pi over 2, this denominator is going to be its biggest. So you're going to find one of its vertices there. So it's going to be 9 divided by 3/2 sine of pi over 2. What's the sine of pi over 2?
1.
1. So this is really 2/2 plus 3/2. Basically, it's going to be 5/2. So you're going to get 18 over 5, which is about 3.6. So there'll be one extreme. Now, the other extreme is you instead of making this a positive 1, if you made this a negative 1, the denominator is going to be as small as it could get. So that's going to happen at theta equals 3 pi over 2. So if we do that, we get 9 over 1 plus 3 pi, or it's going to be 3 over 2 times sine of 3 pi over 2. Instead of a 1 that we got here, here we're going to get negative 1. We'll end up with 9 over negative 1/2, which is negative 18. Let me remind you about plotting something like this. When you plot stuff like this, r and theta, and that is supposed to be an r. When you plot r and theta, if you have a negative radius, it's really like adding 180 degrees or pi to your angle. So if I had positive 18 and 3 pi over 2, 3 pi over 2 is my angle, and I move a distance of 18. But because I got a negative radius, then I have to add pi over 2 to my angle, and it's actually going to plot up here at 18. And that would be negative 18 and 3 pi over 2. Let's compare that to the graph that we see on Desmos. Well, looking at the scale,
Yep.
right up here on your axis, a distance of about 18, you're seeing one of the vertices. And then at a distance of about 3.6, you're seeing the other vertex. So it looks good.
Where did you, I'm kind of confused on where you got pi over 2 and 3 pi over 2 from.
Great question. Let me remind you about the graphs of the sine function. So y equals sine of x. And let's just put in a little scale here to help us out of pi. So remember that the largest that the sine function can be is right here. That's the biggest that the sine function can be, is at, for instance, pi over 2. The smallest that the sine function can be is here. So sine at pi over 2 is 1, sine at 3 pi over 2 is negative 1. So I chose those extremes to plug into my graph in order to figure out where the vertices were. Does that help out?
Yeah.
Okay, good. Anything else on this one? All right. Two more examples. Let's look at r equals 2 over 1 minus cosine of theta. And let me ask you the same questions, except in a different order. Eccentricity, type, and directrix. I'm hoping that we can knock off two of these pretty quickly. So, someone help me out here. What's the eccentricity?
1, maybe 1.
Yep. It's not really written, but it's understood to be a 1. E equals 1. All right. If E equals 1, what type of conic section is this?
Parabola.
Thank you. A parabola. And finally, we need to figure out the directrix. Remember, that term up there is E times D. So, well, 2 equals E times D. Well, when E is 1, that makes things pretty simple. I get D is 2. But there's one last little detail that I got to plug in. I got to figure out, well, is it X equals this, Y equals this, positive, negative, what have you. So let's start with this part first. Is my directrix going to have an X or a Y? Cosine goes with which coordinate, X or Y?
X.
X, thank you. It's going to be X. Good. Now someone else. Is it going to be positive or negative?
Negative.
Negative, because they're going to match. So it's going to be negative 2. Hey. Now we're also going to take a look at the vertex, see if we can't figure out what that's going to be. Vertex. And for that, let me remind you of the graph of the cosine. So before I go to the graph of the cosine, are we okay with these first 3 conclusions?
I had a quick question, actually.
Yeah, please.
So the eccentricity, we ignored, I guess, the sign. So because I saw you just put 1, I thought it was going to be -1 for a second.
Good question. No, eccentricity is going to be between 0 and 1. So where you're going to ignore the sign or use the absolute value. Yes, good question. So let's look at the cosine. Y equals cosine X. And I can show off the graph of the sine here real quick. Now, if I wanted to make my denominator in this as big as possible, so that way the radius is as small as possible and I'm as close to my focus as I can be, how am I going to do that? What's going to make this denominator as big as possible? What value do I want to hit for cosine?
Pi.
Pi. Excellent. Because you'd have at cosine, or cosine of pi, well, cosine of pi is going to be -1. So right down here, cosine of pi is -1. And then in our denominator, you'll have 1 minus -1 will be 2. That's as large as the denominator can be and as small as this ratio can be. So at pi, at theta equal pi, then let's figure out what r is. R is going to be 2 over 1 minus cosine of pi, or 2 over 1 minus negative 1. 2 over 2 is 1. So you get the point 1 and pi. Should be on our graph of 1 over 2, or excuse me, of 2 divided by 1 minus cosine of theta. That should be the vertex. Let's see that real quick. So we'll shut this one off. We'll do R equals 2 divided by 1 minus cosine of theta. You got to go fishing for if you hit the little keypad, and then A, B, and C, theta will be one of your choices. So looks pretty good. If I change things up, put this on a grid like that, you can see at the angle pi, you're at a radial distance of 1 from your focus, which is at 0, 0. So all looking pretty good. Any more follow-up on example C here? Now there's one equation that you should write down and have it handy. I wouldn't be surprised to do something like this on an exam. It's not a really tough equation. It's just the equation of orbits. So polar equation of orbits. I remember one time trying to Google it, trying to figure this stuff out. I wanted to write the polar equation for Earth's orbit. I was just really struggling. So here it is. R equals A times 1 minus E squared over 1 plus E cosine of theta. Now E is going to be the eccentricity. And A is going to be the length of the major semi-axis. All right, might rather to write it or say it different, semi-major axis. Now, obviously, these kind of things would have to be given to you, or some kind of information upon which you can derive it. I'll give you two choices. So maybe you've seen in the nighttime sky recently Comet Neowise. So it was discovered in March of this year. So we can calculate its orbit and come up with a polar equation for its orbit, or we can deal with Earth's orbit. Doesn't matter. Fine either way. Comet Neowise, it is. All right, good choice. Appreciate that. Thank you. So there's two things we need to know about Comet Neowise. And I think I hinted at one of these things earlier. Comet Neowise has a really, really eccentric orbit. Its eccentricity is 0.99921. That's really, really narrow. That makes it what's called a long period comet. Won't be back for thousands of years. And A, length of its major semi-axis, 270. That's going to be astronomical units. We'll just leave it like that. Astronomical units is the distance between Earth and the Sun, about 93 million miles, 149.6 million kilometers. So, okay, not so bad. Let's put it in and see what we get. And we get R is 270 times 1 minus 0.99921 squared divided by 1 plus 0.99921 cosine of theta. And I probably wouldn't mind it if you clean this up a little bit in the numerator. So let's do that. Let's see. Is it worth storing this and then squaring it that way? Nah, probably not. We're only gonna need this once. 270, parentheses, 1 minus 0.99921. Hit the squared key on a right parenthesis. Wow. Yeah, all right. I guess that makes sense. I mean, this is almost going to be 1, so there's hardly going to be anything left here. All right. So if we round it to, say, the 10,000th place, that would be R equals 0.4264 over 1 plus 0.99921 cosine of theta. For a moment, that surprised me that we got something so small, but and looking back at it, I think we're good. So not too bad, not too bad. And I think there's one problem like this at the end of your homework, and I hope this makes it easy. Any questions on that one? Let's see. Yeah, so there's your highly eccentric orbit right there, and I believe there you go. There's comet NEOWISE itself. All right, here's a good place to stop here.